Hello, and welcome to a nonlinear buckling analysis tutorial in ANSYS Workbench. In buckling analysis, there are two general types. First of all, there's linear buckling analysis, and this is based on linear elastic assumptions. The material obeys Hooke's law, and the deformations are small, and the material is in the elastic region of the stress-strain curve. Eigenvalue buckling is based on linear buckling analysis. Eigenvalue buckling is a very common approach to solving buckling problems numerically. It's a quick approach that does not require a lot of computation time. The thing that you need to be careful with is that eigenvalue buckling typically does not represent the actual buckling load in real-world designs. The eigenvalue buckling approach over predicts the critical buckling load. It kind of lives in this perfect world and gives you an optimal or a overestimated critical buckling load. After linear buckling, there's nonlinear buckling, and this accounts for nonlinearities in the material. It accounts for geometric imperfections. It accounts for large deflections, and the solution that you get is typically much lower, depending on the situation, lower than the answer that you get from an eigenvalue or linear buckling analysis. So with that introduction, we'll go ahead and start with the introduction to doing nonlinear buckling in ANSYS Workbench. Nonlinear buckling consists of three steps. First, we'll do a linear static structural analysis. The material can be linear or nonlinear, but we will do a static small displacement type analysis, linearly elastic analysis in a static module. After that, we will perform an eigenvalue buckling analysis to get an estimate of the maximum critical buckling load. Then we will do a nonlinear static structural analysis. And what we do here is we gradually increase a static load until we can't get convergence anymore, and that then becomes our critical buckling load at the point where the solution becomes nonlinear. We'll talk a little bit more about this nonlinear module and the steps taken in the development of that model when we get to it in the process. So let's begin with the static structural and the eigenvalue buckling process. So after opening ANSYS Workbench, I drop a static structural module into my project schematic window. The first thing I'm going to do is double click on engineering data and then click on engineering data sources, and I'm going to come over here to the data sources and scroll down until I find general nonlinear materials. I'll click on that, and then ANSYS shows me a list of nonlinear materials that it has in its general library. I'm going to pick structural steel NL, where the NL stands for nonlinear. I'm going to click the plus sign and add the book. Now it's been added as one of my material choices. I can come down here and double click on it and look at the properties if I would like to and see what they are. So now that I have these loaded, I can come back up here to engineering data sources and see that I have structural steel and nonlinear structural steel added to my model. So I can close this, and then just to make sure everything's updated, I like to click on update the project. and that'll add the material model to it. The other thing I like to do is come to the units and make sure that for this case I'm working in US customary or US engineering. So now I'm ready to bring in my geometry. You can see I've got my green check mark there. I've already opened space claim and I've created this I-beam. The I-beam is 120 inches long, and the cross section is such that we have a 4-inch flange along the top that's a 1/4 of an inch thick. This web here is 5.75 inches long and a 1/4 inch thick. So this is the I-beam that we will be doing our analysis on. Now that I've already uploaded that, I can minimize this window and I can open up mechanical, and you can see that my geometry has been brought in to mechanical, and I'm ready to do my first linear structural analysis. To begin with, I'm just going to check my geometry. So click that. I can see that I have one solid body. I can see that the assignment is structural steel. I'm going to go ahead and change this to the nonlinear structural steel. In my eigenvalue buckling analysis problem or solution, this will not make any difference because nonlinear effects are not included, but this will now be in my model throughout the rest of my choices, and it will be there when I go to pick my nonlinear module for my last step. I'll go ahead and just leave the nonlinear effects and thermal strains on. Again, they won't affect the eigenvalue solution. Everything else there is okay, so I can go ahead and minimize the geometry window. If I just open my materials, I can see that I have my structural steel and my nonlinear structural steel. Everything there's okay. I'm ready to go ahead and mesh this. I'm going to click on sizing and probably increase the resolution from the default 2 up to a 6. I want a fairly dense mesh here, so I'll go ahead and enter a 6 there, and I'll hit update and generate the mesh and see if that looks about like the mesh that I would like. It looks okay. It's not great. It could be a little more fine, but I'll try this mesh for now. So I'm ready to come to the static structural, and I'll insert my boundary conditions. I'm going to put a fixed support over on this face, and I'll click on the face select, click that face and put in the fixed support. So I'll come here to apply. Now I have a fixed end on that face. Now what I want to do on my applied load is apply a load in the Z direction on this face. But you need to be careful when you apply forces to faces. The force remains in the direction of the face. So if you get some bending here and the face is no longer perpendicular, the force will go with that. And so putting face or forces on faces is a little tricky when you go to do a buckling analysis. You're often better to put the forces as discrete point loads at various parts in the I-beam. So I'll apply the loads at key points because those loads remain in the direction that they are assigned. So coming back to static structural, I'll go to loads, I'll put in a force, and I'm going to click the key point right there, control click the key point in the corners of this I-beam. So I'll click there, I'll click here, and I'll click there. So I have those 4 corners, and now I can go ahead and apply that. It says I've got 4 vertices. I'm going to change the force definition from vector to components. I'll leave everything 0 but the Z, and I'm going to enter a -1 there. And I'm going to enter that -1 because then when I go to compute my eigenvalue buckling loads, I will compute the lambda, or the multiplier, and that multiplier will be the critical buckling load. I won't have to come back and multiply it by a static load of something different than 1. So when I'm doing a buckling analysis, I usually put this critical, or this static load in the first module equal to a -1 to give it a compressive unit load. So now I've got that entered. I can go ahead and hit enter. You can see that I've got green check marks all the way through now. I'm going to go to my solution. I'm going to look at a total deformation. I'm going to look at a directional, and I'll look at the directional in the z-axis. So I'll come here and click on z-axis. I'll look at a strain and look at an equivalent von Mises strain. I'll look at the von Mises stress. I could come back and put a probe on and look at a force reaction, and I'll do that. And the boundary condition that I'll put in there will be the fixed support. So I'll click on fixed support and have that boundary condition. So that'll probably do for now for my static model. I'll go ahead and solve this. So I have my solution, I have my force reaction. You can see it increases. My equivalent stress, I have high stress up at the free end, and you can see that I'm starting to get some large deformations there, kind of some different ends. You can see how those static loads have affected that area. And so I might want to rethink how I'm applying those loads. Then I'll come to the strain, the directional deformation. This, if I look at this deformation, I can see that I'm 0 back here at my fixed end, and my largest values are up here. I'm still very small, so this is 1.298 e to the -6 in terms of inches. So that's very small, and that should be because I applied the unit load. I can look at my total deformation and see now that I get positive values, but I'm 0 here at the fixed end again based on the blue, and largest on the end up here. So my static model looks okay. I've got convergence. I'm ready to go ahead and introduce my eigenvalue buckling module. So I'll come back to workbench. I'll come up to eigenvalue buckling. And now when you bring it over here, you can drop it on any one of these modules, but I want to make sure that I come down and take the solution from my static structural into my eigenvalue buckling module. So as I'm holding down and dragging the eigenvalue buckling module from the toolbox tree, I'm going to release the left mouse button when I am on solution, and that will link everything into my eigenvalue buckling module. And you can see I've transferred my data, my geometry, the model, and also the solution is into the setup. Now when I come back to mechanical, I can see that the eigenvalue buckling module has been inserted. Now I'm going to come here and look at the pre-stress. I shouldn't need to change anything here. Pre-stress environment is nonlinear static structural, and that's just because I've got a nonlinear material in there. It will essentially do a linear analysis. I'll come to analysis settings. The maximum number of modes defined is a default of 2. I like to change this at least to 6, and I'm going to go ahead and go 8 modes in this case. I'll keep the pre-stress load pattern, and this will come back and be helpful when I go to do nonlinear buckling analysis. So with that, I'm okay. I don't need to put in any displacement outputs. I can get those easier after the solution has been obtained. So I'll go ahead and solve this. This is usually a pretty quick response. The eigenvalue process is a very quick solution, and the static structure will take a minute in this case because I have a few number of elements. So I'll pause this while it solves. So I've got a green check mark. I have my solution. I can click on solution. Over here I can see my load multiplier values. If I click on the first one and then right click, I can select all. And then if I right click again, I can click on create mode shape results, and you can see that it generates these total deformations for the 8 mode shapes that I've been looking at, or that I asked it to look at. I can hit this solve and these become green check marks almost instantaneously. I can look at my first mode of buckling, and I have my fixed end here, and I can see that this free end is moving back and forth in this direction. If I look along the y-axis, I can see it's bending like that. If I look at my second mode, now I can see that it looked the same, but if I go ahead and do the bending on it, I can see that it's bending in the other direction. So this is a stronger axis. The first mode was the weaker axis, bending like this. I can see the difference in the values. I actually ran some MATLAB code to check these values. Here I had 13,000. In my MATLAB code, I had 15,000. So not right on, but this is Euler buckling, and this over here is eigenvalue buckling, so I'm at least in the ballpark. With this, I'm ready to go ahead and start my final static structural module. So I'll come back to the workbench page and drag and drop my static structural module. Before starting the nonlinear static module, it's good to review what needs to go into that module and how it's different than the first one. So a nonlinear buckling analysis uses a nonlinear static analysis and gradually increases the loads, and we search for the load level at which the structure becomes unstable. And so the solution will not converge. It will converge and converge up till buckling occurs, and then we'll get an unconverged solution. And we want to find that point where the solution can no longer converge. So it's similar to a linear analysis, but there are some differences. First of all, we have either a small force or a geometric imperfection to induce the buckling. And these are required to help initiate the buckling. So we call them either a forced-based nonlinear buckling or a geometry or displacement-based nonlinear buckling. In the force-based, the applied static load should be slightly higher than the load predicted by the eigenvalue buckling analysis, because we know that that eigenvalue buckling prediction overestimates the actual buckling load. So we know we should be unconverged or hit an unconverged solution by that point. In displacement-based buckling, we typically use the first mode computed from the eigenvalue buckling analysis, and we give it a displacement that then is used, and we become nonlinear when we hit that certain displacement. In nonlinear buckling, we need to make sure that the analysis is run with large deformation turned on, and we need to make sure we plot the results for enough load steps so we can verify when the buckling could have occurred. And this can be a little tricky because there are other reasons why the solution may become unconverged instead of just a buckling. So usually what you want to look for in a typical buckling curve is we plot the force and the deflection, and we'll be linear for a while, and then we begin to go nonlinear, And actually, when the slope of the force deflection curve becomes horizontal or flat, then we have our unconverged solution break off of that, and this point right here would be our critical buckling load. This plot is really clear and nice. It's always not this clear when we do a typical buckling analysis. For some cases that induce a non-converged solution, we have a force deflection plot and we see we load linearly and then go nonlinear, everything looking just fine. But then the slope of this force deflection curve does not go to zero, and we still break off with an unconverged solution. This can be more of a or of a numerical instability instead of a buckling instability or physical instability. So we want to look for more of a force deflection curve like this and a horizontal slope compared to a slope with some value to it. But again, these are kind of tricky to look at, and it's nice to look at the deformed structure as well as these force deflection plots. So we'll look at doing this now in Workbench. So I'll bring in my static structural module, come over here, left click, drag it. Now I'm not going to hover over anything here because I don't want to bring all of these things into my nonlinear module. So I'll drop it, and now I certainly can pass on the engineering data. So I'll go ahead and connect the engineering data because I've set that up with my nonlinear data. And I want to connect the solution from my eigenvalue buckling problem to my model in my nonlinear module. So I'll go ahead and click on solution and drag it to model and drop it. And now you can see that the geometry's gone, and the geometry that I'll be using is going to be the deformed geometry from the eigenvalue buckling problem. So I now can come up to view, and if I click on view and come down and show properties, I can come over here and click on my static structural, and I can see the properties of that solution. And if you look at engineering data and these different things, you can come down and see the properties for those different solutions. If I click on the solution to the eigenvalue buckling problem, I can see that the solution is looking at a scale. Well, first of all, the mode. This is the mode shape of the buckling that I want to look at. And here I've got a value of 1, so I'm looking at the first mode. And this is a scale multiplier. So if I come back to mechanical and I look at the first mode buckling, I can see that my value up here is a maximum value of 1. So I've got a 1-inch displacement out here, a unit magnitude, and it's 1 inch because that's what my units are in. Now if I want that to be my starting deformed geometry, that's okay. If I wanted it to be 2 inches or 3 inches, whatever, all I would need to do is come back to Workbench, click on this, and increase the deformed or the scale factor, and I could enter in a value of 2 or whatever I wanted it to be. The other thing that you might need to do before you can open your model is to do an update project. So once you've created this static structural, you need to do an update project and pass everything through into your model. So after opening mechanical for this portion of the model, we can see that geometry imports has a lightning bolt on it. That'll be okay because our geometry has a green check mark, and we don't need to do anything with this lightning bolt. We bring in our geometry and we can see that it's using the eigenvalue buckling deformed geometry. If you move your geometry around and look at it, you can see the very slight deformation that we have. You can see this end curves down just a little bit. It curves down 1 inch over 120. And so we can see our geometry deformation there. Then we can come to our materials, and we've got our structural steel. We can come back up to geometry and just make sure that we're using our structural steel nonlinear down here. We can close these menu items. We can click on our mesh, and our mesh is the same as it was for the initial static, and it's not overly fine, but it's sufficient for what we're doing here. Then I come to static analysis, and under static analysis I can enter in my boundary conditions. And on the end over here I've set up a fixed support. So I've got A as a fixed support, and that's A over here. On B I have a force, and what I have done is I've gone in and put forces at key points. And so you can see that the key points I have selected are the corners of the I-beam, these internal corners. I selected 4 of those, so those 4 vertices have a load of 0 in X, 0 in Y, and minus 14,000 as a total load. And this 14,000 comes from the predicted 13,000 for the critical buckling load in the eigenvalue buckling system. So this should be plenty of force that is being applied to cause this beam to buckle. In analysis settings, I can click on this, and what I have done here is I've changed the set time to 100 to 16,000 seconds, and I usually set this close to what the force is. So I could have come here, and instead of going 16,000, I could have put 14,000 in my analysis settings. But this then gives me a second for each load increment. I turn auto time stepping on, and I wanted to have a fine detailed curve. So I had initial substeps of 50, a minimum substeps of 50, and a maximum of 100. These are often set to 20, but I wanted to increase the resolution here. Then you need to make sure that you come down and turn large deflection analysis on. So under analysis settings, we turn on the large deflection analysis. Now I come to my solution, and I want to determine what outputs I want. So I often look at a total deformation and then deformation in the X, Y, and Z axes. You can also look at equivalent elastic strain, plastic strain, total, and then I always look at equivalent stress. And if we want to plot a force deflection curve, we need to add the force reaction. This is done under probe. So you can click on probe and come down here and see the force reaction. And so that's how the force reaction was listed here as an output. Then we can build a chart. To build this chart, you simply come up under the solution context and click on chart, and this will set the chart right here. When we click on this, we can see that it has 2 objects. The 2 objects I've picked are the forced reaction and the directional displacement in the Z direction. It asked me for the x-axis, and so if I click on this, I can see that I could make the x-axis time, directional deformation in minimum, maximum, or any of the force reactions. I used the directional deformation in the 3 direction. And these will all be computed over here as your tabular data that you can turn on and off as you want to look at your results. You can label your axes, X and Y, right here. And oftentimes I want to omit the time plot so you can display it, but the default is to display it. I usually click this to omit. And I leave all these as display so that I can look at them if I want to. but I can also deselect them when I have my results. Then you go ahead and you run the solution and you hope it doesn't converge. And what you get are these red lightning bolts saying that your solution has not converged. If you come down to your messages and double click on messages, you will also see the error that the solver engine was unable to converge a solution for the nonlinear problem, and that's what was expected. So now we can go through and begin to look at our results. So to increase the resolution, I came back to analysis settings and increased this time from 16,000 to 20,000 seconds. Then I reran the model. And you can see here that actually total deformation, Z deformation, and equivalent stress all converged. And we can look at those and they appear to provide good results, believable results. These others with red lightning bolts did not converge. If we come to our chart, we are plotting force displacement chart. So vertical axis is the force, horizontal is deflection in inches. You can see that we start out down here and go pretty well nonlinear. And then at a force of 10,500, we don't converge anymore and we stop. If we come over and look at our data, we can see all our deformations and we can plot these different force reactions and deformations, and by clicking on and off, they'll show up in the plot or not. If we come up to equivalent stress, for example, we can see that in terms of minimum and maximum and average PSI, we're going along okay. If we turn the average and the minimum off, here's our maximum. If we come along here at 15,000, we have a huge jump and pretty much go just straight with no increase, but a huge increase in time with no data points in between here. If we look at our deformation in the X direction, we can see that we're coming, or excuse me, the Y direction is we're coming along here, we're looking pretty nonlinear, and then all of a sudden at this 15,000, we go horizontal. So we know something's happening at this time step. You need to make sure that you realize this is not force, but that this is seconds. So if we come over to our data and we scroll down to 15,000, here's our 15,000, and we can come along and see what those values are. If we actually look at our force reaction and go to the 15,000 time limit, we can see that all that occurred at a force reaction of 10,500, which is what we saw over here in our chart with a maximum load of 10,500. So based on this analysis and doing a nonlinear buckling analysis, we can see that the actual buckling load is 10,500 based on a load or force nonlinear buckling analysis compared to the eigenvalue buckling analysis, where we obtained a value of 13,000 or so. So our force has gone down as we expected, and it's gone down about like we would expect. So with this, we'll go ahead and do a nonlinear displacement-based buckling analysis. So we'll come back to Workbench and we'll enter in a new static structural module that we'll do a displacement-based analysis on. So coming over here to static structure, I'll left click, bring it over and drop it as a standalone system. I can create the engineering data or connect the engineering data from the previous models into this model. And then I can also import the results from the eigenvalue buckling into this model, and I'll transfer that term into model. And you can see now that I've got my force-based and my displacement-based analysis. I need to do a model update to incorporate that. And one thing I could come back and consider is if I want to increase or decrease this scale factor. I'm still going to look at first mode buckling, but I could increase that and buckle more quickly. I'll go ahead and leave it at 1 for now. I'll come up and click Update Project, and then I'll come and double click on Model and open up my deformed geometry based model. Going through the displacement based approach, if we open up our project tree, I've solved this problem already. If we look at our geometry, it's brought in as the eigenvalue buckling, same as before. Nothing has changed here from the previous static model. Our mesh is exactly the same. We didn't have to redo any of that. I came down here to static structural analysis settings. I changed the step time up to 40,000 to get a few more steps, and I increased the initial sub-steps and minimum to 60, and I made sure that large deflection was on. I applied a fixed support at this end like we've been doing with this model, and I applied a remote displacement on this face. I applied the remote displacement of negative 0.5 inches, and it was ramped. I applied it on this face right here. I didn't have any rotation. I just had a pure deformation of minus 0.5 inches in the Z direction. And I saw that that would cause buckling because back in the force-based model, if you look at the solution here, I don't have it solved now because I've changed some things, but the maximum displacement was about 1/4 of an inch. So coming over to this module and giving it a half of an inch made sure that we would indeed deform. So if we look at the results, we can come to the chart, and in the chart, the two objects I have plotted are the force reaction and the Z deformation. So down here's the deformation in Z, and here is the applied load. And you can see that I begin to apply the load's increasing, my deflection's increasing, everything looks fine here. I plateau, I hit a peak at 10,567, and if you remember in our force-based nonlinear buckling approach, we had a force of 10,500. So this approximates that very well. After I hit this peak, you can see that the deflection continues to increase, but the load carrying capability of the beam decreases as that deflection continues to increase. I can look at the equivalent stress, and what you need to do when you're doing this is oftentimes when you click on this outline selection, it's waiting for an answer here. So when you click on these other things, they won't show up. So you need to hit cancel there. Make sure you're just seeing the two objects. Then when you come to these other components, they'll plot as expected. So there's the equivalent stress. It looks like it should. We can animate this and see how it deforms. We can look at the deformation in the other axes and see how those appear. We can look at elastic and plastic strain. So again, to summarize, we have a chart here that shows us our critical buckling load is this peak at 10,567. In the force-based module, we got a critical buckling load of 10,500. And in our eigenvalue buckling process, we had a critical buckling load of about 13,000. So I hope this 3-step tutorial has helped you and provides insight for you to continue on now with your buckling analysis. Thanks for watching.